Everyone, thank you for coming back yet again for the third class. Um, Excellent. So as I was just mentioning, so in previous classes, and I like to go over some of the stuff that we did in the previous classes. Just, I think about this stuff a lot. Some of you may only think about it once a week in this class, and it could be you don't even catch all of them. So I think it's good to go over some of these. So the first thing that we did is we spent some time going over some different use cases, as I mentioned before, of some various digital assets, and how they could exist in the real world. So, for example, on the top left, we have credentials. One of the problems with the credential system today is that, similar to a lot of things, they exist within centralized databases at the institutions that that what's the word? Not distribute them, but issue them, I guess. And in many cases, those institutions might not exist forever. And getting access to them is a little bit, could be difficult. I know that, when I had to go back to grad school and I had to get actual, the actual stamped copies or whatever of my various transcripts, it was certainly an annoying process whereby it makes much more sense. And there's already use cases that are being developed that you would own your own digital asset, which would have within it your credential, verified on the blockchain that it was not distributed, but issued by a specific institution at a specific time to you, whatever it happens to mean, whether it's the grades that you had or any tests or any other important information relevant to that. But then you could own that, you could have access to that and bring it wherever that you wanted. At the top right, we mentioned gaming. Gaming is a really interesting example because in gaming, you have both non-fungible tokens, traditional NFTs. For example, within a game, you might have a specific tool, which might be unique, or you might have a specific, some kind of feature, whether a sword or an animal or a piece of clothing. But you also might have money in a game that you use to buy various things, and that wouldn't be that wouldn't be non-fungible, right? That would be completely fungible, just like most of the money that we have in the physical world. And then also we mentioned that there's various applications for mortgages and also tickets to events. And these are not the only use cases. I just wanted to, as much as I could, drive home the idea that digital assets, firstly, are very practical within a lot of the things that we do and experience and use within the physical world in business and in our lives. And also, because of that, as these things get adopted, it's going to be even more important to understand these things, sooner rather than later. And then moving forward, I don't know if I can get rid of this. I don't know why it's there, but nonetheless, one of the things that we spoke about is how physical assets and digital assets are essentially opposite from each other. By that, I mean, physical assets, you understand that they are yours because you have them protected in your bank account, your wallet, your house, your coffers. There's an asset that exists and it's yours by, as they say, ownership is 9/10 of the law, right? If it's in your house, if it's in your possession, that's how you know that you own it. Digital assets, however, are the exact opposite. You don't actually put a digital asset into anything, but instead you stamp your name, you engrave your name onto and within the digital asset so that you are the only person that can use it, that can access it, that can transfer it to other people. So now the question becomes, how does this all work? And really, who gets paid and how? Al Gutman will hopefully watch this video. He asked during the first class, who maintains the blockchain or any particular blockchain? And the answer right here is crypto miners. So, okay, I've heard of crypto miners. I know what mining is in the world. You dig in the ground, you find gold, silver, whatever it is, maybe diamonds. I'm not really sure how that goes, how that explains Bitcoin, but I do know that they use a similar word. Let's figure it out. So firstly, what is a blockchain? very, very generic, not a specific one. What is a concept of a blockchain? Really, it's just a very, very large transaction ledger. So here is just a ledger. I wanted to put an example because I didn't want to assume what people's backgrounds were, either in accounting or just finance or ledgers in general. So here we just have an image of a bunch of transactions within some account. And essentially that's what a blockchain is. The only difference is that a blockchain is very, 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 very big. And instead of just being related to one particular transaction, it has every single transaction that has ever been transacted with that blockchain. So, for example, the Bitcoin blockchain within the text of the blockchain has every transaction that every person or entity has done throughout time. I'm going to stop there. Does anybody have any questions? No hands up. Keep going. Awesome.
Wait,
I'm stopping.
how do you do a hands up?
Well, you just talked and now I can hear you.
So what does this mean? A blockchain it's a digital record of transactions that pertain to a specific a digital virtual, in this case, coin, correct?
For right now, let's say yes.
Okay.
What it really is a record of transactions that were transacted on that blockchain. Now, the specific difference is that when you get into digital assets, a digital asset like an NFT, right, which again could be a ticket. So I could buy a ticket to, for example, a Mavericks game, and I mentioned Mavericks because from the first class, Mark Cuban has already said that the Mavericks are going to be issuing NFTs for their tickets. And I went into why and how that's going to happen in the first class. So if I were to buy a ticket, an NFT to a Mavericks game, that NFT was built on a specific blockchain, whether it's on Bitcoin, whether it's on Ethereum, whether it's on Flow, whether it's on Cardano, etc. So the transaction related to that ticket will also be within the transaction ledger for the specific blockchain on which it was built. Does that make sense?
Sure.
Okay.
And how does Mr. Cuban arrange for his tickets to be posted on a particular blockchain? And maybe that was Al's question. Who gets paid? Like, does Mark calls up such and such a blockchain and says, "Hey, I want to post my thousands of Maverick tickets, several times a week through the basketball season on you. What will it cost me?"
So we're not going to specifically get into that right. I didn't. Well, we might. I didn't actually plan to, but the answer is firstly, there really is no, and we just have to wrap our minds around this. There really is no person to call. So yeah. Let's go back and forth a little bit. On the left here, we have the traditional banking system that we all know and love, or maybe we don't love and maybe we don't know, but nonetheless, it is the traditional banking system, a centralized ledger. So if you think about, for example, I do my personal and some of my business banking at Wells Fargo. So here in the center, we can think that we have Wells Fargo, and then around it are businesses, some, other entities, maybe a governmental entity, and maybe, individuals. And they're all sending their transactions into Wells Fargo, send money over here, deposit this, pay this bill, take this fee out for my annual fee for, I don't know, maintaining my checking account, why I would have to have a fee on that, whatever it is. And then Wells Fargo takes all of those transactions and they put them onto their general ledger. And they maintain that general ledger, and they hire auditors, outside auditors, to verify that what's on that general ledger is correct, so that, among other things, investors and people can invest in Wells Fargo or Bank of America or Commerce or TD Bank or whatever bank, and be confident that those transactions represent truth and they have a good idea of what's going on in that system. So that is the centralized ledger system. A decentralized system is where no one specific central entity controls what is put onto the ledger. And so essentially, all of these individual entities all act as auditors, verifying that they all have true and correct copies of the blockchain ledger. So essentially, when you decide to be a miner on a specific blockchain, for example, Bitcoin, you install various technology, various programs, you download the entire copy of the Bitcoin public ledger. Yes, it takes a while. And then you spend the rest of the time, among other things, auditing and verifying that your copy is in, matches every other copy that exists for any other person or entity that has decided to be a blockchain miner. So let's get a little bit more into how that works. So firstly, let's understand, or even to just inform you, that the origin of digital assets owes a lot to spam email. In the early 90s, spam email was, I suppose, rampant, and people didn't like it. So they said, how can we come up with a system by which we can limit spam? So they said, okay, I have an idea. What if we require everybody who is sending an email to solve a function? And in order to do that, it's going to take some processing power, right? Some energy to like turn on the lights or, to run your computer, fine. But it won't take a lot of energy. It won't take a lot of power. So if you wanted to send an email to me, or I wanted to send an email to you, and I was required to solve some very rudimentary function in order to do that, I can do that, fine, no problem, and it would get sent to you. However, if I wanted to send out 1 million emails, well, then I wouldn't have a little bit of computational power that I would have to spend, but I would have a lot, and it at that point wouldn't become financially viable for me to do that, and I wouldn't send that spam email. Now, this concept within email essentially failed. It's not used very much for lots of reasons, none the least of which is that we have verified email mailing lists where people subscribe to them, and just because you're very popular and have a large subscription to your newsletter doesn't mean that you should be penalized by having to spend a lot of computing power and hence money just in order to send those emails. So within the email system, it hasn't been effective. However, the concept of requiring a proof of work in order to send a message has found a home within digital assets, at least at the early stages and even today. So let's understand how a transaction gets into a blockchain and how this proof of work fits in here. And then we'll also see specifically why we hear sometimes about environmental problems, and also how proof of stake attempts to combat that, and also some of the things that might be detrimental about that. So, or at least not detrimental, but everything has pluses and minuses. Nothing is perfect. And we shouldn't think that proof of stake is perfect. We shouldn't say proof of work is horrible. Proof of stake is great. We should say proof of work was very beneficial because it's, rudimentary and revolutionary in bringing us this technology. Proof of stake is better, and other things will come. Very nice. Okay, so let's go through this right here. And we're going to go slow, and please ask any questions that you have. So firstly, a transaction is entered into the network and a fee is specified. You say, I would like to buy a ticket to the Mavericks game. I'm willing to spend whatever it is that they charge me. And here is a fee that I'm willing to give in order for that transaction to be processed. Those transactions are brought into the network and they are distributed to various miners. Once enough transactions come in, that form 1 megabyte of data, they're called a block. Why? Because if we had to add transactions to the blockchain, transaction by transaction by transaction, it would be so much work. It really would be very, very cumbersome. So in order to change that, at least with Bitcoin, they've said that each block is going to be 1 megabyte of data. Fine, we take a bunch of transactions that have not yet been verified, we put them into a block, and now here comes the data mining. So all the miners, they're called nodes often, but essentially we can think of them as miners or computers or whatever it happens to be. They get all these transactions, they're now made into a block. Now they have to do this work that I discussed before. So what is it? So there's something called, we don't need to get too much into how it works because I don't know how relevant it will be, and I want to make sure that we understand the concepts, but essentially we have this thing called a hash function. A hash function takes in two inputs, two numbers, and gives out one number. And there is no way to understand what the output will be from the input. You can't work backwards to solve it. The only way to come up with the answer that you want is to guess. So what you do is you take two numbers. One of them is called a challenge number. That just comes from the previous chain. We don't need to worry about that. And then each miner is going to guess. It is completely a guess. It is nothing more than that at a number which is called a proof. And what happens is this proof gets added to the challenge, put into this function, and a number comes out. The goal is that the number that comes out should have a whole bunch of zeros at the beginning and then some numbers at the end. So and essentially you want the number to be as low as possible. And once you have found the number that you're looking for, let me go back. Each block has a certain target that needs to be, the answer to the hash function needs to be less than that target in order to be considered a valid proof. Now, a couple things. Firstly, and if this is too much in the weeds, I apologize. Firstly, there's more than one number there's more than one proof number that will solve the equation. So it's not a unique number. And also, we're not looking for an exact number. We're just looking for a number less than a certain number. Now, why is it that we're looking for something so non-specific? Because we really don't care about solving the equation. What we do is we care that the miner has done sufficient work to prove that they are processing valid transactions as opposed to not processing valid transactions. Now, once the proof has been found, that node, that miner, which finds that proof, distributes the proof, the answer, to all the other nodes. Those nodes take that proof and the challenge, put it into the hash function. They look, they see the answer is correct, and they say, gee shucks, this miner won and we didn't win. Now, for winning, the miner that successfully guessed the proof gets, number one, all of the fees that were within that block. Whatever was said at the beginning, any fees that were paid, that person gets them, or excuse me, that miner gets them. Addition to that, within Bitcoin and other blockchains, they also get a reward of additional Bitcoin. At this point, that is the genesis, essentially, of the term mining. The way in which additional Bitcoin is brought out into the system is a reward for mining these transactions. Now, you might see here that I put in bold and red, the other miners who also did work get nothing. And that's important because that is the origin and that is the reason why you'll hear so much in the news about, oh my goodness, crypto mining is the worst ecological disaster that has ever been unleashed upon the world. And maybe in the short term, there actually is something to be said for that. Why do I say that? Because if you have a lot of miners trying to process blocks, so only one is going to win. So great. The processing power used to mine that block for that winning miner was probably not so significant, and it was worth it to process that transaction. But the other 999 miners who spent computational power on that transaction got nothing. So if you think about the amount of energy used to process a single block, it's actually very large. And that is why you'll hear about all of these environmental issues. We'll get to that a little more later in a couple minutes, but I wanted to bring that out. So great. Now that a miner has found this A proof, which comes out with a result below the given target, so that they've proven that they've done some work, they validate that their proof number is correct with all the other nodes, and then that block, essentially that group of transactions, gets listed onto the blockchain, gets added as another block in the chain, and as I mentioned, the miner gets a reward, a certain amount of Bitcoin for successfully verifying the block, and they get all the fees. Once that block is now added to the blockchain is now distributed to all of the nodes. So again, like we said before, everybody's auditing, everybody has the same copy of the blockchain ledger, and the transaction is complete. Any questions right now? Oh, I see that there are some.
Yeah. Here's a quickie, maybe. How large are those fees relative to the value of a coin?
It's a very, very good question, and there really is no answer specifically. And the reason there is no answer is because it's going to depend on a lot of things. Number one, how many miners are available? Number two, how many transactions are trying to be processed at any given period of time, right? If there are not a lot of transactions that need to be processed, so the fee for them will be less because you don't need to process your transaction over any other transaction. However, if there are a lot of transactions, you might not make it into the first block. You might have to wait till the second block, depending on what the fee you're willing to pay is. And you'll see within certain systems, for example, I think MetaMask has this, maybe some other ones, maybe they all do actually, that you can specify either a high, a medium, or a low fee to try to prioritize your transaction. Eventually, usually it will get done, except if it takes a significant period of time and then it gets rejected. You don't necessarily lose anything, you just didn't get your transaction done. But I hope that answers your question.
Could just maybe a little bit of scale. So let's say a Bitcoin right now is $30,000.
Yeah.
Is a fee $10? Is it $1,000? Any kind of context at all? Theoretical, approximated context would be helpful.
I honestly, the crypto space, the digital space is an interesting space. I don't even think I would have a decent range for you. The thing that I will tell you though, is that it has nothing to do with the size of the amount of the transaction. It only has to do with your interest in the transaction and the number of miners that are able to mine it, right? The fact that Bitcoin is 30-something thousand does not mean that the fee is going to be greater, right? Because you could transact something on the Bitcoin blockchain that is either worth many, many Bitcoin, or that's worth a couple Satoshis, which is a fraction of a Bitcoin. And the fee would not be determined on that amount. The fee would be determined on, the computational power, at least within the Bitcoin community, the computational power required to process the transaction. I wish it was based on the value. It just doesn't happen to be. But what you're saying is an interesting point, because you have to, it's important to be thoughtful about how you're structuring your transactions and when you're structuring your transactions. And for example, one of the things, and this is going a little bit further afield, but one of the things to think about, if we go back here, right, if we go back here, so this is a little bit true. I mean, it's true, but I didn't make it 100%. Let me just say what I mean. I have more than one digital wallet. So when it says here, this is the exclusive property of Benjamin E. Milch, it doesn't put my name. It puts the name of my digital wallet, puts the address of my digital wallet. Now, the difference is that to transfer it from one digital wallet to another digital wallet, even if it's my own asset, costs a fee. Why? Because I'm adding a transaction to the ledger, right? So for that reason, it's very important to be mindful of when you're processing transactions and what you want to process and how. Then we can get into transactions that are processed on and off chain, which we will, but for right now, if it's okay, I don't want to get too into the weeds on that. Does that help?
Yeah, I'm accumulating perspective. Thank you. I'll let you keep going. It's great.
Ask any
Thank you.
questions. Ask any question you have. Excellent.
Well, yeah. So just like transacting in an equity or a bond, there's maybe in the past more than now, a transaction to move an asset, to buy an asset, to sell would engage also a fee that would need to be paid to the intermediary. And effectively, perhaps, we're saying that to create an item in a blockchain will require some kind of an incentive to be paid to those out there. There are zillions of guys running computers who want to be providing the service of becoming the home for a block. So,
that's correct.
Yeah, okay.
The difference is that in a centralized system, like at Wells Fargo, they will charge you for various things like making sure they have enough pencils and making sure that the lights go on and making sure that their tellers have, insurance or whatever it happens to be. Whereas within a digital asset community, you're paying the amount of money that it will cost, that it will be beneficial for a miner to incentivize them to add it to a blockchain, and then that's it. And since there's a competitive nature to that, it should hypothetically be lower than you'd pay other places. Now, again, that's not always true because there are different numbers of miners and different amounts of transactions and things like that. But certainly steady state, that is the goal. Now, one of the things that I should mention here, we'll get into more in subsequent sessions, is right here, down here where it says the miner that successfully finds a proof gets a reward and all the fees. Different digital assets have different protocols, making them either limited resources or non-limited resources. So for example, Bitcoin, like gold or platinum, is a limited resource. The protocol of Bitcoin says that there will be only 21 million total Bitcoin. As we go throughout time, the reward for successfully validating a block gets less and less. And by approximately 2040 or so, all of the Bitcoins that will ever be in existence should be mined. At that point, the only reward for mining a block will be the fees from the transactions and not any kind of reward. Ethereum, which is a different blockchain, which is on still on proof of work, but moving to proof of stake, is not a limited resource. And similar to USD, they can issue additional Ethereum at any point.
Ben, did you see my question?
I did not, but I will hear it.
So in number 3 up there, is a computer guessing or is a person guessing? And is it random? Or I know what you said, it was random, but is a computer guessing randomly or is a person guessing randomly to get the?
A computer is guessing randomly. And that's why it's costing. That's where the computational power comes from, because essentially, yeah, and it's also why gamers are so mad, if you've heard about that, because essentially what
pure luck. You're saying it's basically luck.
It is luck, 100%.
Oh, got it.
That's 100%.
Okay. By the way, how does a person know they won? They got it.
So the way that they know that they got is the given target that you're trying to get under is known at the beginning, right? So you take your proof and you put it into the hash function, and then the hash function comes out with an answer. If the answer is less than that target, you win. If it doesn't, you try again.
Got it.
Yeah.
Thanks.
That's why, they say you're solving a mathematical equation, and to some degree you are, but the mathematical equation really has no meaning. It's just proving that you have spent the computational power that means that you wouldn't be putting nefarious transactions in because it wouldn't be financially advantageous for you to do. And also, if you tried to add that to the blockchain, all of the other nodes would invalidate that transaction because they would say either these transactions don't match the transactions that I've been given, or this account doesn't actually have the ability to make this transaction, or the proof that you've used does not actually solve the function. One of those things.
Thanks.
Excellent. So, lest we think that anything is perfect in the world, there are always potential problems in any one of these scenarios. So I mentioned, for example, in a proof of work protocol like Bitcoin, the chances of being successful, if you think about it, are commensurate with your computing power as a percentage of the total computing power within the network at any one period of time, right? The total amount of power you have to be able to process transactions. So whereas in a proof of work, a proof of stake protocol like Ethereum, the transactions you are able to verify are commensurate with the percentage of staked Ethereum that you own. So for example, if you own 3% of, if you're a data miner and you own Ethereum and you say, I'm going to stake X amount of Ethereum, meaning I'm going to hold it and use that as a means of proving the stake of Ethereum that I have. If I have 3% of all the staked Ethereum, I should have the ability to mine 3% of the transactions that come in. Now, what this does is it lowers, obviously, the computational power required to process transactions, because you don't have every miner trying to process every transaction at any period of time and one being successful and all of the other ones not being successful. However, you have a problem in both cases. One of the problems is called the 51% attack problem. And essentially what this problem is the risk that any one miner or group of miners will have 51% of the power. So within the Bitcoin community, that would essentially be 51% of the computational power. If any miner had a majority share of the computational power, they would have the ability to add and verify a majority of the transactions. So even if they put in a nefarious transaction and had put in a proof that was not effective, when the other nodes rejected it, by having a 51% majority, that would override all of the other nodes, and essentially that miner could put transactions that say, yeah, all of Ben Milch's money now gets sent to me. In a proof of stake, this is also hypothetically possible. How? If you have 51% of all of the staked Ethereum, for example, so similarly also, you could be able to verify only the transactions that you wanted and ignore any of the other transactions. At this point in time, 2021, particularly within some of the bigger digital assets like Bitcoin and Ethereum, it's really not a problem realistically. The 51% problem was a problem 7 or 8 years ago, I think in 2014 within Bitcoin, because there weren't as many miners, and there was one mining pool that got close to but never achieved 51%. And certainly within a proof of stake platform, certainly one that's very large, it would be very, very cumbersome, very, very difficult to have 51% of all the staked currency at any one time. But it's just important to mention because as we look at all of these things, we have to understand the pluses and minuses to them, and understand, if nothing else, that these things will grow and evolve because we find better and more efficient ways to handle these problems and to process transactions and things like that. In the next minute and 41 seconds, anybody have a question?
Yeah, so some breakthrough lab with some kind of quantum computing power.
Yes.
That's way superior to anything else that exists.
Yes.
And those are being developed. They could potentially subvert the system.
At this point, no. Because the reason I'm saying that is because no one person is developing that, right? Many people are trying to continually get higher and higher computing power, and unless they all decide to come together in a kumbaya state, which is exactly the opposite of the right idea. So they're just competing with each other, either from a stake perspective or from a computational power perspective. So yes, if I decide to buy a really fancy, graphics card and things like that to create, to put together a data mining, or excuse me, a crypto mining rig, I could do that. I would probably get, not very successful because of this. But at this point in time, I think at least within Bitcoin and Ethereum and things like that, they're just too big realistically for anybody to
But
get.
what if it's a government? What if it's a government entity with vast resources, and that says it, vast resources and an intent to subvert.
Like I said, these risks are certainly real, and